Hi guys, today we're going to talk about Kirchhoff's rules, and you may be wondering, what is this about? I mean, maybe you found yourself really into Ohm's law here, and you just can't imagine something else coming to you that would be just as useful. We can't use Ohm's law alone here because when you take a look at this circuit, these elements, for example, like the battery and R3, at first you might, question, hey, are these in series? Are these in parallel? I'm really not sure. But take a look at what happens here. We know that I1 is going to be moving to the right here through this top battery. And then we'll have I1 coming down this branch here. But what ends up happening is at this junction, this meeting point where these two branches come together, you have I1 and I2 coming together at this junction. So when I have junctions on my circuit, I usually label them with capital J and then a subscript. So I'll make this junction A, for example, and junction B. But so I1 and I2 come together at junction B, and we get I3 as a result. So notice that even though at first glance maybe you thought that battery and R3 were in series, that they're not. The current's not the same here. So this requires us to have some knowledge of Kirchhoff's rules here. So the first rule in terms of Kirchhoff's rule is called the junction rule. And a lot of you have already applied this rule on your own because you knew about this idea of conservation of charge. Okay, so the junction rule is just another application of conservation of charge. And what it says is that at a junction, the current into the junction must equal the current out of the junction. So for example, if I want to use Kirchhoff's junction rule for junction B, I can do that. Let me take a look at the currents coming in. That would be I1 plus I2, and the current going out would be I3. And I could write a statement for junction A as well. So let me see, the currents coming in are going to be I3, and the currents going out are going to be I2 right here, and I1 moving upwards. Aren't these two statements pretty much saying the same thing? Yes. Yes, they are. So if we had some knowns here for two of these currents, we could find the missing one. And we'll take a look at an example for that in a moment. The second of Kirchhoff's rules is called the loop rule. And the loop rule is an application of conservation of energy. So in the junction rule, we talked about current. For the loop rule, we're going to be talking about delta V, or the potential difference. So with the loop rule, what we're saying is for any closed loop, the delta V must equal 0. So when I'm thinking about the loop rule, first thing I like to do is take a look at the circuit and try to figure out if I can know the direction of any of the currents. And sometimes this can be hard to do if you have a multi-loop circuit and you don't necessarily know the potential difference across the batteries. In the example problem I have coming next, I have an example problem where the current through the middle branch will be to the right, and that's why I chose to do that for this example. So once you do that, the first thing I like to do is I find the closed loops. Okay, once I do that, the next step for me is to find any resistors or batteries, any circuit elements that can change the electric potential. So for example, I like to follow the same direction as the current because I know that if the electric potential decreases, like it would across a resistor or a light bulb. I know that if the electric potential decreases, when it comes to the loop rule, I will subtract. So when I'm moving from an area, for example, of high electric potential to lower electric potential, I'm going to subtract that in terms of the loop rule. And if the electric potential increases because of that particular circuit element, like for example, when you go from the negative terminal of a battery through the battery to the positive terminal, you're experiencing an increase in the electric potential. So if the electric potential increases, as it would through a battery, we know that we'll be adding that value. So let me give you an example here of how to apply the loop rule. You can start anywhere in your circuit. So again, we had these junctions that we talked about before, this junction B and junction A. I'm going to put them in there for reference points. So again, totally up to you where you want to start. If we start at junction B, for example, we know that there's current going down and then through resistor 3, across this battery, up this branch. And now once you get to junction A, some of the current will go to the right through the middle branch, and some of the current will go upwards. So we have some options here. So I'm going to finish this first loop that I found. That current will go through resistor 2, and now I'm back where I started from. So I have a complete closed loop. I'm going to name this loop loop 1. All right, so second loop that we pretty much already found was if I start at junction B again, and you can start anywhere you want, but I'm going to start at junction B again. I could go down through resistor 3, through this bottom battery, and instead of the current making a right at junction A this time, we're going to go straight up through resistor 1, through the top battery, down this branch, and back where we started from. So we have another closed loop, and I'll name that loop loop 2. So now let's take a look at how we can apply loop rule. So loop rule for loop 1, first thing I do is I think about where I'm starting from, and I go to every circuit element and I decide if that's going to be a drop or an add here. So as current goes through R3, so I'm going with the direction of current here in this bottom green loop. Sorry about that. I'm going to have a voltage drop. So I'm going to do subtract delta V across R3. The next element that I'm hitting is this battery, and that's going to be an increase in electric potential. So let's add delta V of that battery. Now we're coming on up. We're not hitting anything until current goes through R2. That'll be a voltage drop, so minus delta V through R2. And I'm back where I'm starting from, so this whole statement should equal 0 volts. In the next video, I'm going to show you how we can now use Ohm's law to find any unknowns we don't have. Let's do the loop rule for loop 2. I'm going to start in this same spot here, and we come down. We're going to need, again, delta V across R3. That's going to be subtraction. We're getting to a battery, so we're going to add the delta V across the battery. Now we're going to go up this branch. Okay, we need the delta V across R1. We know that the electric potential will decrease as a result of going through the resistor, so let's subtract delta V R1. We'll go through the top battery, so that's going to be an addition, delta V top battery. Coming back down, and we're back where we started, so equals 0 volts.